Hello, Honor Chem students. Mrs. Snyder here, wanting to do the second part of the lesson, which is calculating freezing point depression problems. Freezing point depression, again, is a colligative property, and here's just a diagram of what we have for ice. You can see that there's hydrogen bonding here, holding those molecules really close together. And what happens if we put a salt on the ice, the water will want to dissolve the solute, and it disrupts that hydrogen bonding and makes it slushy, and that's what actually will melt the ice, and why it's such a great tool to use here in Minnesota for our sidewalks and our streets and things like that. So how do we calculate a freezing point depression problem? Well, again, we would have to calculate a delta T, and a delta T is based on a constant, which is a Kf, times the molality times the number of particles. And once you calculate that change in temperature of the freezing point, you can then use the freezing point of solution is equal to the freezing point of pure solvent minus the delta T, and that's why we call that a freezing point depression. And again, we're going to use this paper, which you should have attached to the bottom of this lesson, that you should print out or at least have access to when you do your homework and also when you do the exam. Okay, so let's take a look at what a typical freezing point practice would look like. Here it says find the freezing point of a 0.1, and again I meant that to make that 3 sig figs just to try to stay consistent. So I'm going to go ahead and add the sig figs in on that. It's a 0.100. So this is now going to be 0. It's not working yet. No, it's because I don't have a color on. So let's make that here. We're going to make this 0.1100 molal solution. Okay, so instead of the 0.1, I want it 0.100. There we go. Okay, and the solution is potassium sulfate. You should assume that the solution is water when they tell you, if they just say solution, just assume it's water unless they tell you otherwise. So here you would take potassium sulfate, and now remember that potassium sulfate will dissociate into 3 particles. You get 2 potassiums and 1 sulfate particle. So that's a total of 3. And what you're going to do is we're going to then know that the freezing point of the solution is going to be the freezing point of the pure solvent minus the delta T. So what happens here is we are going to calculate the delta T, and the delta T is going to use the Kf. And since my solvent is water, I'm going to look at the water here, and the Kf for water is 1.86 degrees C over little m. The molality was given to us, it's 0.100 m, and the number of particles is 3. So when I do that work, it ends up being 0.558 degrees C. I then am going to plug that into whatever the freezing point is of the solvent. Well, in this case, it's water, and the freezing point of water is 0 degrees C. And I'm going to subtract the delta T that I calculated here, and that gives me a freezing point of solution of negative 0.558 degrees C. So that is how you calculate a freezing point depression problem. Okay, your homework is going to have some particles that are ionic, and they also could have some things that are covalent. So you do have to pay attention to your counting particles. So when you have an ionic compound, you count the number of particles, just like I did here. This is an ionic compound. I would strongly recommend that you write the dissociation equation and you can count the number of particles. So this has 2 and the sulfate is 1, so that's what gave me a total of 3. If we look back at what we were doing with boiling point, here we had 1 of the sodium, and there should be a negative here on the chloride, 1 sodium ion, 1 chloride ion, so this is a total of 2 particles. So you should count the particles if it's ionic. But when you have a molecular compound, such as sugar, and sugar doesn't dissociate, so it doesn't break up, then the number of particles is 1. So anything that has covalent bonding will be what we call molecular, and it will have the number of particles dissociating as 1. It won't be like the ionic compounds where you have to count how many ions are in solutions. For molecular compounds, it will be 1. And again, how are you going to know that it's a molecular compound? Do you remember? How are you going to know it's ionic? Do you remember? A molecular compound is things that are all nonmetals. An ionic compound will have a metal and a nonmetal. So here's an example that's in your homework. I'm not going to do the problem, but I'm just going to give you kind of a watch out for. Here it's asking you to find the boiling point of each of the following solutions. So you have 0.50 moles of glucose, and then they give you the formula here, right? C6H12O6, right? And it is in 1,000 grams of water. Notice that this is C6H12O6. That's all molecular. So that means it's a covalent compound, and the number of particles when you figure out this delta T will be 1. Compared to here, sodium chloride is an ionic compound, and then you're going to have to count the number of particles. So that's an important thing to make note of. The last thing I want to talk about, and this is just real generally, because you've heard of this term osmosis. I know that you guys had talked about this in biology. And osmosis is the movement of a substance through a semi-permeable membrane. And osmosis is part of, or actually osmotic pressure, is actually part of what we would call a colligative property. Osmotic pressure is the external pressure needed to be applied to stop the natural phenomena of osmosis. So here I have a U-tube, and in this U-tube you'll notice that there is a solution with some solute and solvent, and then here I have just pure water, pure solvent, and there's a semi-permeable membrane. Now you know from biology that water is going to be attracted to the solute to dissolve it. So over time, this is actually what happens, is that the water molecule is going to be attracted to the solute, and you're going to get this uneven levels of water, pure water here versus solution in the U-tube compared to what you had here. And that's all because of this water movement through this semi-permeable membrane. Okay, so now what osmotic pressure is what if we apply a force here, and a lot of this has to do with biology, and it's important for, like, when you get an IV, that the IV bag, the concentration is exactly the same as your cellular concentration. And what they do is they apply this pressure so that you are retaining, again, that constant level. Okay, so you stop that osmosis from naturally happening. So this is actually a pressure that is applied. Okay, so pressure. And that is what osmotic pressure is. It's the external pressure needed to apply, that you apply to stop osmosis. Now, the question is, what if we went ahead and added a whole bunch more than just that natural amount needed to stop osmosis? So what if we added, and here my computer's just did a little crazy thing here, so hopefully, what if we added a whole bunch of pressure? So let's just go here, and we're going to add a whole bunch of pressure. So if we add a whole bunch of pressure, then that means we could force pure water to go through that semi-permeable membrane. So what if we could force all of this to go back to pure water? And that is called reverse osmosis, also known as RO. Okay, and RO you may have heard of before, reverse osmosis. It is the reason why we have what we call desalination plants. Okay, desalination plants are along a coast. California has them. The Middle East has them. Dubai has them. They wouldn't be able to have the city of Dubai if they did not have the desalination plants. And what they do is they actually intake seawater and they go through this RO system with the semi-permeable membrane, and they apply high pressure and they get pure water coming out from that. It takes a lot of energy to do, but it is available, and it is a way that they can have a water source right next to the sea. Okay, aircraft carriers or cruise ships, you may not have thought of that either. They need to have reverse osmosis systems in their ship so that the sailors, which by the way, an aircraft carrier can carry a couple thousand people, about the size of our high school, out to sea. Well, they need water in order for those sailors to survive. And they can do that process with a smaller version of an RO system, but it would be enough to maintain water for those sailors. So that's a little bit about RO and how to calculate a freezing point depression problem. If you have any questions, don't hesitate to reach out and ask. Have a great day. See you guys later.